Every year, the world produces billions of square feet of veneer, a petal-thin material hiding the strength and beauty of entire forests. Picture this. From a single log, you can get enough surface area to cover a football field. That's exactly why this industry is worth over $40 billion annually. From one perfect American walnut log, about 3 feet in diameter, you get anywhere from 10,000 to 30,000 square feet of unique surface. One log, almost an entire football field of veneer. Using veneer cuts the need to harvest valuable tree species by 98% compared to making furniture from solid wood. Instead of cutting down 20 trees to make 20 tables, you can harvest one perfect tree and leave the other 19 growing in the forest. But what's behind that number? How does an ordinary tree go through spa treatments, fiery tunnels, and encounters with scalpel-sharp blades to become luxury furniture? Watch closely. At the end, you'll discover a secret almost nobody realizes. Picture a lumber mill that specializes in veneer production. Massive logs of premium hardwoods, oak, ash, maple, walnut, cherry, arrive here by truck. But not every tree makes the cut. These have to be perfectly straight, tall trees with large trunk diameters, and most importantly, free of knots, cracks, and other defects for a significant height. Every knot is a scar that ruins the perfect grain pattern. That's why only the finest specimens are chosen for a veneer. When one of these perfect logs arrives at the mill, it doesn't go straight to the blade. First, it gets the industrial spa treatment. The logs are submerged in enormous pools of hot water or placed in special chambers filled with hot steam. This isn't about cleanliness. This process, lasting anywhere from several hours to several days, at temperatures around 212 degrees Fahrenheit, does two crucial things. It softens the wood, making it more pliable and cooperative for cutting, and it transforms its color, making it richer and more uniform. After the hot bath, the bark gets stripped from the log. A special machine peels away the rough outer shell, revealing clean wood underneath. And now comes the most critical moment before the main show: centering. The log gets locked into the machine, and an operator uses lasers to find its perfect axis of rotation. This is absolutely crucial. Giant pencil in a giant sharpener. The log starts spinning around its axis, and the blade cuts into the spinning wood and starts shaving off a continuous wide ribbon of veneer, just 1/50th to 1/8 of an inch thick. It's like unrolling a paper towel roll. An endless, wet, flexible sheet comes out of the machine, which is then cut into pieces of the right size. This method is highly productive, but it creates a characteristic, chaotic pattern that isn't always valued in high-end furniture. The second method, used to obtain the most beautiful decorative veneer, is called slicing. This isn't a sharpener anymore. It's the world's biggest cheese slicer. Here, a log, or part of it cut into beams, is firmly secured to a movable platform. Above it, or to the side, sits a massive, sharp blade. The platform with the wood moves back and forth, or up and down, and with each pass, the blade shaves off a single, perfectly flat sheet of veneer. It's a slower, less productive process, but it's what gives you that refined, linear, or figured grain pattern we value so much in expensive furniture. Depending on exactly how the log was cut before slicing, you can get different types of patterns: radial, tangential, mimicking the look of solid plank. Freshly cut veneer, no matter the method, is called green. It's soaking wet, flexible like damp paper, and tears easily. It needs to dry. The ribbons or sheets of veneer are carefully fed into a long drying chamber. Think of it as a giant tunnel oven, where the veneer slowly moves along on rollers or a mesh conveyor. Hot air circulates inside, gently and evenly pulling moisture out. The process is tightly controlled. Dry it too fast and the veneer will crack or buckle. Within minutes, that wet, floppy sheet becomes dry, slightly brittle but stable. After drying, the veneer sheets have ragged edges. They're stacked high and sent under a massive guillotine. A sharp blade slams down and in one stroke slices off the rough bits, creating perfectly straight edges. Now the sheets are ready for the most critical stage, where it's not machines doing the work, it's people with trained eyes. This is sorting. Specialists carefully inspect each sheet, evaluating its color, grain pattern, and any defects, then sort them into bundles by grade. It's meticulous work because this determines the veneer's price and application. But individual veneer sheets are often too narrow for making something like a tabletop, so they need to be joined into one large panel. This process is called stitching or splicing. Two sheets with perfectly straight edges are fed into a special machine. It presses them tightly together, and a specialized mechanism bonds them. This could be a thin zigzag line of adhesive or a glued paper tape. The result? A large, continuous veneer sheet, ready to be applied to a substrate. Now for some history. Using thin layers of wood goes back thousands of years. Ancient Egyptians used veneer to decorate sarcophagi and furniture 3,000 years ago. But modern industrial veneer production only began in the 19th century with the invention of steam engines and precision machinery. The first veneer peeling lathes appeared in the mid-19th century and revolutionized the furniture industry. Instead of sawing valuable wood species into thick boards and losing most of the material to sawdust, manufacturers could now obtain ultra-thin sheets, maximizing every inch of the log. The global veneer market is a massive industry, turning over more than $40 billion a year. The largest producers are China, the US, Germany, Italy, and Indonesia. Veneer isn't just for furniture. It's used in making doors, musical instruments, yacht interiors, luxury car interiors, and premium space finishes. But the most important application is plywood. Yes, ordinary plywood as we know it is multiple layers of veneer glued together with perpendicular grain direction. This exact structure gives plywood its strength and resistance to warping. And now the most impressive number behind veneer, its efficiency rating. Take one massive, perfectly straight log of premium American walnut, several yards long and about 3 feet across. If you just sawed it into boards, you could make, say, one big table and a few chairs. Now here's the kicker. If you slice that same log into veneer just 24 thousandths of an inch thick, you can get anywhere from 10,000 to 30,000 square feet of unique surface. To put that in perspective, that's enough to cover almost an entire football field from a single log. Using veneer cuts the need to harvest precious hardwoods by 98% compared to making solid wood furniture. Meaning instead of cutting down 20 trees to build 20 tables, we can harvest one perfect tree and leave the other 19 growing in the forest. This makes veneer one of the most environmentally responsible ways to use wood. But veneer has another hidden advantage that few people think about. The thing is, the most beautiful, unique wood grain patterns are often found in the most unusual parts of a tree, where the trunk branches out, in burls, in the root section. If you saw a tree like that into boards, these areas often end up as scrap because they're too small or irregularly shaped. But with veneer production, even a small section with a unique pattern can be turned into several square meters of luxurious material. There are entire categories of exclusive veneer made from burls, wood growths with incredibly complex, swirling patterns. One burl the size of a soccer ball can yield enough veneer to finish an entire study, and this veneer can cost thousands of dollars per square meter. There's even a market for archive veneer, material made from trees cut down decades or even centuries ago and stored in warehouses. Some species of wood that are now protected or extinct can only be found in the form of this archive veneer.
Veneer manufacturing technology is constantly evolving. Modern machines are equipped with laser scanning systems that analyze the log structure before cutting and select the optimal angle and method to produce the most beautiful grain pattern. Computer control allows sheets less than half a millimeter thick to be sliced with precision down to hundredths of an inch. New processing methods are being developed that enable veneer to be stained, embossed with textures, and made to imitate rare species. And so, after journeying from a majestic tree in the forest through a hot bath at 200 degrees Fahrenheit, past a knife sharp as a scalpel, and through the fiery tunnel of a dryer, this material emerges, thin as a petal, carrying all the beauty, history, and unique character of the forest, ready to bring a piece of it into our homes. These billions of dollars aren't just money, they're proof that beauty and practicality can walk hand in hand, allowing us to enjoy nature's unique patterns without causing irreparable harm. Every sheet of veneer is a thin slice of a tree's history, one that lived for decades or centuries and is now ready to serve humanity for centuries more in the form of beautiful furniture.
A poisonous metal that saves lives. Sounds paradoxical, but it's true. Lead, one of the most toxic elements on Earth. It poisoned Roman emperors, killed thousands of workers, got banned from paint and gasoline. But without it, not a single car on the planet would start. Every second, the world produces 2 tons of lead. 85% goes into batteries, the heart of every vehicle. Lead shields doctors from X-rays and stops radiation at nuclear plants. The heaviest common metal you can hold in your hands, 11 grams per cubic centimeter. How do you get a bluish metal that kills and saves at the same time from silver ore? You'll find out why the Roman Empire fell because of lead pipes, how a lead-acid battery works, and why this ancient poison is still irreplaceable today. Watch till the end. The finale reveals the dark side of progress. This is the story of a metal humanity can neither embrace nor let go.
Lead's story begins deep in ancient times. About 7,000 years ago, people learned to smelt lead from ore. It was one of the first metals humans extracted from stone. Lead melts at a low temperature, just 627 degrees Fahrenheit. Even a campfire can melt lead ore. The ancient Egyptians used lead to make statuettes and cosmetics. Yes, women lined their eyes with lead-based white paint. The Roman Empire took lead use to absurd levels. Lead water pipes stretched throughout Rome. Wine was stored in lead amphorae. The metal made the drink sweeter. Wealthy Romans ate from lead dishes. Aristocracy sweetened wine with lead sugar, lead acetate, which actually tastes sweet. The result? Mass poisonings. Roman nobility suffered from gout, insanity, infertility. Many historians believe lead poisoning of the elite became one of the causes of Rome's fall. Emperor Nero, known for his madness, may have been poisoned by lead since childhood. In the Middle Ages, lead was used to make cathedral roofs, stained glass windows, and printing type. Alchemists considered lead the basest of metals and tried to turn it into gold. The 19th century brought a boom in the lead industry. Lead white became the foundation for paints, bright, durable, cheap. Lead-coated toys, furniture, house walls. Children gnawed on lead toys and died from poisoning. Workers at lead plants perished by the dozens. Metal dust destroyed their nervous systems. In the 20th century, lead was added to gasoline as an anti-knock additive. Tetraethyl lead boosted octane ratings. Engines ran smoother. But exhaust fumes poisoned cities. By century's end, leaded gasoline was banned almost everywhere. Lead paints were banned too. Lead pipes replaced with plastic. It seemed the age of lead was over. But no, lead production kept growing because a new massive application emerged: car batteries. Where does lead come from today? The primary lead mineral is galena, lead sulfide, cube-shaped crystals, silvery gray with a metallic luster, extremely heavy, density of about 0.27 pounds per cubic inch. Galena often occurs alongside silver, zinc, copper. The largest deposits are found in China, Australia, the USA, Peru, Mexico. China produces half the world's lead, around 6 million tons per year. Lead is extracted through open-pit mining in quarries or underground mines. They blast the rock, crush it, grind it. The result is ore containing 3 to 10% lead. That's enough for industrial processing. The ore is enriched through flotation. Crushed ore is mixed with water and special reagents. Galena particles stick to air bubbles and float up, forming foam. Waste rock gets washed away. The concentrate contains up to 70.
Lead concentrate gets roasted in massive furnaces at around 1800 degrees Fahrenheit. Lead sulfide transforms into lead oxide, releasing sulfur dioxide gas. They capture this gas and use it to make sulfuric acid. Nothing goes to waste. Lead oxide gets mixed with coke and fluxes, limestone or quartz. Loaded into a shaft furnace. Hot air blasts in from below. Temperature climbs to 2200 degrees. Carbon reduces the lead oxide back to metal. Molten lead pools at the bottom of the furnace, a heavy gray-blue liquid. Lead is 11 times denser than water. Drop a steel ball into molten lead and it'll float right on the surface. They tap the melt from the furnace into ladles. The melt's still impure, contains copper, zinc, silver, gold. Yeah, lead ore often carries precious metals. Extracting them pays for part of production. Lead gets refined, purified. Heat it to 900 degrees and add zinc. Silver and gold dissolve in the zinc and float up. They skim them off. The purified lead gets poured into ingots. A standard ingot weighs about 55 pounds and is the size of a brick, but it weighs like a bag of cement. Try lifting it. Lead is heavy and soft. You can cut it with a knife, scratch it with your fingernail. At room temperature, lead develops a dull oxide film, loses its shine. A fresh cut is silvery blue, beautiful, but goes dull within a minute. Lead doesn't rust in the usual sense. The oxide film protects the metal from further corrosion. That's why Roman lead pipes have survived 2,000 years. But the key property of lead is its toxicity. Lead and its compounds are poisonous. Once it enters the body, lead accumulates in bones, replacing calcium. It destroys the nervous system, causes anemia, damages kidneys and brain. Especially dangerous for children. Even tiny doses disrupt nervous system development. There is no safe level of lead in blood. Any amount is harmful. That's why working with lead demands the strictest safety measures: respirators, protective clothing, showers after every shift.
But if lead is so toxic, why do they keep producing it in such massive quantities? Because lead has properties that simply can't be replaced. First, its weight. Lead is 1.5 times heavier than iron. Second, it's soft and easy to work with. Third, it blocks radiation. Gamma rays and X-rays are absorbed by lead better than any other affordable metal. Only gold and tungsten are better, but they're way too expensive. So lead gets used for radiation protection. X-ray room walls are lined with lead sheets. Doctors and technicians wear lead aprons. Weigh about 10 pounds, uncomfortable, but they protect. Containers for transporting radioactive materials are made from lead several inches thick. At nuclear power plants, lead is used in shielding systems. Viewing windows for observing reactors are made from leaded glass, transparent, but contains up to 70% lead oxide. This glass stops radiation while letting light through. Without lead, nuclear medicine and power wouldn't be possible. But the main use of lead? Batteries. 85% of global lead production goes into lead-acid batteries. These are the most common type of battery on the planet. Every car with an internal combustion engine has one. 1 billion cars means 1 billion lead batteries. How does it work? Inside a plastic case, there are plates made of lead and lead dioxide submerged in sulfuric acid. During discharge, the lead and lead dioxide react with the acid, forming lead sulfate and water. Electrical energy is released. During charging, the process reverses. Electricity converts the lead sulfate back into metal and dioxide. This cycle can repeat hundreds of times. Lead-acid batteries are reliable, cheap, and can handle high currents. Perfect for starting an engine. A starter motor draws hundreds of amps. Lithium-ion batteries can't compete in this application yet. One car battery contains between 22 and 33 pounds of lead. It lasts 3 to 5 years, then gets recycled. Lead is the recycling champion among all materials. Up to 99% of lead from old batteries makes it back into production. An old battery gets dropped off at a collection point where it's disassembled and crushed. Lead plates are melted down, purified, and cast into ingots. A new battery contains up to 80% recycled lead. This makes economic sense. Secondary lead costs less than primary. And it's environmentally sound. No need to dig new mines. Global lead production runs about 12 million tons per year. Roughly half comes from recycled material. Lead prices hover around $2,000 per ton, cheap compared to other metals. Beyond batteries and radiation shielding, lead shows up in cable sheathing, ammunition, fishing weights, and wheel balancing weights, in construction for soundproofing and waterproofing. But these uses are gradually declining as manufacturers hunt for less toxic alternatives. Lead's future lies in batteries and radiation protection. Until someone invents a replacement, lead remains irreplaceable.
And just like that, traveling from silvery galena crystals through the inferno of furnaces at 1200 degrees and complex purification from impurities, lead emerges, the most contradictory metal in human history. A metal that poisoned Roman emperors and saves lives in hospitals. Banned in paints and toys, yet no car starts without it. Heavy, soft, toxic, but irreplaceable. This is the story of progress's dark side, how a poisonous element became the foundation of modern civilization. Every time you turn your ignition key, get an X-ray, or have a chest scan, know this: lead is working for you, shielding you from radiation, storing energy, starting engines. The paradox of a metal that kills when mishandled and saves when used right. 7,000 years alongside humanity, from ancient figurines to modern batteries. Lead is a reminder that progress always has a price, and that price is sometimes written on the periodic table with the symbol Pb, plumbum, from the Latin word meaning heaviness, the weight of choosing between toxicity and necessity. A metal humanity cannot abandon, no matter how hard it tries. But an 80,000-ton press isn't just about aviation and space, it's about energy. Massive shafts for hydroturbines, rotors for nuclear reactors, high-pressure housings, all of this demands single-piece forgings of monstrous proportions. Picture a hydroturbine shaft 50 feet long and over 6 feet in diameter. Its weight, more than 100 tons. You can only forge a component like that on a super powerful press. The blank gets heated in a furnace the size of a house, then a crane transfers it onto the press platen, and in just a few strikes, it's shaped into form. Each strike, 80,000 tons of force molding the metal, densifying its structure, squeezing out internal defects. After forging, the part cools slowly, then undergoes heat treatment and machining, but the foundation of its strength, that's laid right there on the press. $80,000 tons. Picture a force that could crush 10 tanks at once. A machine tall as a 10-story building that transforms a red-hot steel mass weighing hundreds of tons into a flat panel like it's Play-Doh. This isn't science fiction. It's the world's most powerful forging press, operating in China since 2013. 80,000 tons of pressure. That's more than the weight of 50,000 cars crashing down on a piece of metal the size of a table. Why did humanity need such monstrous machines? What secrets hide in their history from the Cold War? How did the USSR create a 75,000-ton monster and the US answer with a 50,000-ton press? You'll discover how these metallurgical giants were born, how this inhuman force works, and what can be done under such pressure. Watch till the end. The finale reveals the scale of what humanity creates. The story of giant forging presses didn't start with peaceful purposes. It started with the Cold War arms race. In the late 40s and early 50s, aviation and rocketry demanded fundamentally new solutions. Aircraft were getting bigger, faster, flying higher. Rockets grew in size. And all of this required enormous single-piece components made from high-strength alloys. Titanium wing spars, aluminum fuselage panels, steel rocket engine parts. Welding these components together from multiple pieces weakened the structure. Welded seams were vulnerable under load and vibration. What was needed was a technology capable of forging a giant part as a single piece, no seams. That's how the idea of ultra-powerful hydraulic presses was born. The United States understood this first and built several presses in the 50s, capable of exerting up to 50,000 tons of force. The Soviet Union wasn't about to be left behind. At the height of the space race and the arms race, the USSR built a 75,000-ton forging press, an absolute record at the time. The giant machine stood in the factory floor like a metal cathedral, dozens of meters tall, hundreds of tons of structure, hydraulic cylinders as thick as a human body. This press allowed the Soviet Union to stamp out parts for rockets, submarines, and aircraft on a scale that was previously impossible. A solid titanium component several meters long, no longer a dream, but reality. 75,000 tons of force meant that metal of any hardness became pliable material. The Cold War fueled technological progress, and these forging giants were one of its symbols. For decades, these presses remained the pinnacle of engineering. But in 2013,
China shattered all records. At one of their metallurgical plants, they fired up a hydraulic press with a force of 80,000 tons. 80,000 tons? That's a force that's hard to wrap your head around. It's the weight of a major ocean liner crashing down on an area the size of a dining table, or pressure equivalent to 50,000 cars stacked on top of each other. The scale of this press is mind-blowing, as tall as a 10-story apartment building, weighing thousands of tons of steel and cast iron, with massive hydraulic systems capable of generating this monstrous force. This press didn't just break a record, it opened up a whole new era of possibilities. Now you can stamp out parts of sizes that used to be considered impossible. Panels for jumbo jets, components for space rockets, reactor equipment, all of this became achievable thanks to this machine. How does a giant like this work? The foundation is hydraulics. Picture massive cylinders filled with oil under monstrous pressure. When pressurized oil flows into the cylinder, the piston starts to move. But this isn't your ordinary piston. Its diameter measures in yards, and its stroke spans dozens of yards. Slowly, but with unimaginable force, the piston descends to where a glowing metal workpiece sits on a massive plate. The workpiece weighs hundreds of tons, a huge ingot of steel, titanium, or aluminum, heated to around 2200 degrees. The metal glows bright orange, radiating unbearable heat. The shop floor fills with the roar of hydraulics, the smell of hot metal and oil. And then the upper plate of the press begins its descent, slowly, almost ceremonially. But behind that calm lies 80,000 tons of force. Contact. The upper plate of the press touches the red-hot blank, and the miracle of deformation begins. Metal that's hard as rock at room temperature starts flowing like thick paste under this kind of pressure. 80,000 tons don't give the metal a choice. The blank flattens, spreads outward, takes the shape of the die. A thick ingot becomes a flat panel or a complex three-dimensional part. The process is accompanied by deafening thunder. The metal cracks, groans, excess material squeezes out, flowing to the sides in glowing streams. Temperature, pressure, force, all controlled by computers with millimeter precision. The slightest mistake and a multi-ton blank is ruined, or worse, the press itself can fail. But the operators know their craft. One stamping cycle takes minutes, but the result is a seamless part with perfect internal structure. Why does this matter so much? Because a single forged part is stronger than any welded structure. A weld seam is always a weak point. Under load, vibration, cyclic stress, that's where cracks start. In aviation or spaceflight, a crack means catastrophe. That's why major structural elements, aircraft wing spars, fuselage panels, landing gear components, rocket engine parts, must be one piece. A super heavy press can forge a titanium beam 30 feet long with no joints whatsoever, or an aluminum panel the size of half a Boeing wing, or a steel blank for reactor equipment weighing 400,000 pounds. Parts like these used to be welded together from dozens of pieces. Now they're made in one press stroke. It's a revolution in manufacturing. China didn't build this press by accident. The country is aggressively developing its aviation industry, space program, and nuclear power. All of this demands technologies that were previously only available to the US and Russia. An 80,000-ton press is a declaration of technological leadership. Now China can manufacture components it used to have to buy from abroad or settle for smaller dimensions. This is strategic independence. When you've got a press like this, you can build your own aircraft, your own rockets, your own reactors without relying on someone else's technology. It's no coincidence that information about the exact specs and capabilities of this press is tightly controlled. This isn't just manufacturing equipment, it's an element of national security and technological sovereignty. There are only a handful of these presses in the world. Russia has kept its Soviet-era 75,000-ton giants, still running in defense plants today. The US operates its 50,000-ton machines, built back in the 50s and 60s. China now leads with 80,000 tons. There are projects for even more powerful presses, 100,000 tons and beyond. But each of these machines represents a colossal investment. Building a super heavy press costs hundreds of millions of dollars. You need a special foundation that goes dozens of feet into the ground. You need massive hydraulic systems, furnaces to heat the billets, cranes with lifting capacities in the hundreds of tons. It's an entire complex covering the area of a football field. But the payoff is worth it, the ability to manufacture parts that nobody else can. And just like that, through the Cold War, through the technology race between superpowers, through decades of engineering development, humanity arrived at the 80,000-ton press. This isn't just a machine, it's a symbol that we've learned to dominate matter with a force comparable to geological processes. When 80,000 tons come crashing down on white-hot metal, it's like watching the Earth's crust crumple into mountains under tectonic plates. Except here, this process is controlled by humans. Every part that comes out of a press like this carries the imprint of unimaginable force and precision. Planes fly, rockets shoot into space, reactors generate power, and behind all of it stand these giant presses, crushing metal like Play-Doh. This is the story of how humanity learned to create the force of gods and use it to conquer the sky, space, and the atom.